Okay, chemistry time. We're going to talk today about covalent bonding and polarity. Covalent bonding and polarity. Let's actually start with polarity because I don't see any reason why not. Let's actually not start with polarity. One, because I don't see any reason why not. And two, because we actually do need to talk about covalent bonding in general. I think you already know what covalent bonding in general is, though, so we're going to briefly touch on that, then go to polarity, then we'll talk about covalent naming, which will be the last thing. So a covalent bond is a bond, as you know from your vocab, that a covalent bond is bonding between two or more atoms, usually, in fact almost always, what kind of atoms? Like nonmetals, almost always nonmetals. Bonding between two or more atoms in which electrons are, it's like a Mad Lib verb. Yeah, thanks Mitch, shared. In which electrons are shared. As opposed to in ionic bonding, which is when what happens? Yeah, the metal has given an electron to the nonmetal, which then has that electron semi-permanently, and then they're held together by the electromagnetic attraction between them, between the positive now cation and the negative now anion. Whereas in this, what's holding them together in this case? Here we have two generic atoms. They're being held together. By what, though?
By their own force.
Which type of force? No, the strong nuclear holds the nuclei, each nucleus with itself. No, weak nucleus governs electromagnetic decay, or sorry, nuclear decay. So what force is left that holds them together? Nope, that ain't it. They're technically attracted to each other with gravity because they technically have mass, but that is almost completely negligible. So what force does hold them together? You're still missing one. Electromagnetic is the guess, yeah. Because here's what happens. So they're sharing some electrons. There's at least one electron in this shared electron cloud. And the electron that is being shared is attracted both to this one through the electromagnetic force, because this is a positively charged nucleus, the electron has a negative charge, and it's also attracted to this one. So what force governs covalent bonding as well? The electromagnetic force. Coffee because I wanted Mitch to suffer the pangs of defeat. But it is compare and contrast ionic and covalent bonds. The comparison is they're both a form of the electromagnetic force. They're both a form of the electromagnetic force. So what's the contrast then? We already talked about this, but in a covalent bond, they're shared. The electron is effectively orbiting, although we know that's not how they actually move. But the electron is effectively orbiting both nuclei, and that's a sharing. Another contrast is that we can have different kind of amounts of bonds. And the stronger a bond gets, the closer the atoms are together. So strong bond equals close together. The strongest bond, I think, that has ever been discovered in the universe is the bond between two nitrogen atoms in the N2 molecule. They're very close together. The nuclei are borderline touching. And this is an example of a triple bond. So this is the N2 molecule. And when I say triple bond, it means that they're sharing, well, you guess. We had talked about this in physical science, so it shouldn't be a whole guess. But how many electrons are being shared in a triple bond? Let's have another guess. Well, how many are being shared in a single bond? A what of electrons has to be shared? You should have read your book, or at least you should have remembered this from physical science. It's a pair of electrons. So there's always a pair of electrons being shared in any covalent bond. And so here we have a triple bond. That means that there are three pairs, so 6 electrons are being shared. So we sometimes draw it in this way. Each nitrogen starts out with how many, I'm going to just draw it this way. No, how many valence electrons? Try one more time, Peter. How many valence electrons does a nitrogen start out with? How many valence electrons? 5. And now you can draw that as on this electron dot diagram as what? An N with 1, 2, 3, 4, 5. We'll put it there. If I have another one, how many BT dub? Oh, I love it when he says that. How many electrons does it want to have?
8.
It wants to have 8. So how many can it share from this bad boy? How many can it share from its twin? 3. Okay, so let's see what happens then. So if each one of them is sharing 3 with the other, we end up with this arrangement. So this one has altogether how many? 1, 2, 3, 4, 5, 6, 7, 8. This one has altogether how many?
8.
So how many are they sharing? 6. They're sharing 6. And so that's in 2, and that's what we call a triple bond. What if we do the same thing with oxygen? Well, I'm going to try to do it over here. We're going to have 2 oxygens. Valence electrons of oxygen? How many? I'm just going to do 1 for now. 1, 2, 3, 4. Just let's do it like that. Okay, here's another oxygen. Come along. 1, 2, 3, 4, 5, 6. Well, how many more does this one need? Can this one give up 2? So how many can they share? Both of them between them. No, try again. If they're each sharing 2, they're going to have a total of 2 pairs. We do try to, and we'll talk, because of something called the valence shell electron pair repulsion theory. Valence shell electron, this is going to be impossible to read, pair repulsion. It's not as bad as I thought it was, actually. Because of the valence shell electron pair repulsion theory, which was one of your vocab words, the electrons try to stay as far apart from each other as they can. So I do draw it like this, where the oxygens, instead of having them like on top and on bottom, the electrons try to stay as far away from each other as they can, because each pair of electrons repels another pair of electrons. We kind of, in classical atomic theory, we think about an individual electron of an up spin, remember up and down spin electrons?
I just have one side comment.
Let's hear the comment.
That is, it's what we learned in, you know.
Oh yeah, you're right. This is because I said
Not an acronym,
it's
because
it
it doesn't make a word.
is an acronym because I pronounced it. I could say Vesper. Some people call it the Vesper theory, and then it would be an acronym. But if I just said VSEPR, then it would be an initialism. Thank you, Peyton. I'm glad you pointed that out. Anyway, I've lost my train of thought. But if you remember top and bottom spin electrons or up and down spin electrons that we did when we did electron configuration. It's in classic atomic theory, those two things attract. So an up and a down electron I should do it like this, kind of go around with each other. That's not quite how it works, but we do think of it that way. So these pairs of electrons repel each other. And so we end up with the different shapes of molecular shape. You need to be somewhat familiar with the shapes of molecules on page 263. So look at that real quick. There's a diagram on page 263. For the sake of the video, you can pause this. I'm going to get an email from Glencoe Science, and they're going to say, copyright infringement, you're going to die. I'm trying to show it to the camera. There it is. You can pause it on that, and you can kind of see the shapes. You need to be familiar with those shapes. And one of them, you remember, the professor on our videos is always talking about a linear molecule. He always has like a dog toy that represents these atoms, you know. And this becomes actually, this is extremely important for bonding, are these shapes. And they're all governed by this valence shell electron pair repulsion theory, which says that the valence electrons in the outermost shell want to repel each other. They try to stay as far away from each other as they can. A neat example you can see, or a simple example on 261. If you have all these balloons, they try to get as far away from you can see the picture on 261. Anyway, so we have now, how would I name this molecule?
Well, it shares
Yeah, so what is this?
double.
This is a double bond.
Oh, Mr. It might be important, but it's okay.
You can go if you need to. So this is a double bond. This molecule is O2, which is just normal oxygen. These two are both examples of what kind of molecules. There are 7 of these that are always this way on the periodic table. Do you remember these? O2 and N2 are both diatomic molecules. Do you remember what the other ones are? You need to write these down and have them memorized. The diatomic molecules, this will become especially important in the next chapter. Diatomic molecules, these are the elements that always exist as 2 of that same atom bonded together, are H2, N2, O2, F2, Cl2, and I2. I'm sorry, I think Br2 is one of them too. There should be 7. 1, 2, 3, 4, 5, 6. Yeah, I2 is one of them. I mean, Br2 is one of them. So there's a pattern here. Hydrogen's up in the top left corner. And then you see nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. A little mnemonic user remembers, if you're looking at the periodic table, those 6 make the number 7. There are 7 of them, and 6 of them make the numbers, or like a rough outline of the numeral 7. So hydrogen's kind of a dot all by itself over there, and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine kind of make a 7. It looks kind of like this. Here's hydrogen, and then those other 6 are down like that. So you can kind of use that to remember. But do you kind of see the idea behind why these exist always this way? Well, we saw for nitrogen that if we have one nitrogen, they're stable with how many? Remember? How many valence electrons are they stable with? 8. Because of what?
The octet.
Because of the octet rule. And so if you have one nitrogen atom, chances are there's other nitrogen atoms around. And so they like to bond with each other. And as I said, this is the strongest bond in the known universe. And so they really, really like to bond together. Same with oxygen, and obviously same with fluorine, chlorine, bromine, iodine. We're going to do one more with, actually let's do 2 more of these with hydrogen and with fluorine. How many valence electrons does hydrogen have? How many valence electrons does hydrogen have? 1. How many does it want to have? 2. Can you see how a bond could form here? Just smoosh them closer. There we go. Now each of them has 2. We end up with H. Oh, and by the way, we draw single bonds as a single line, double bonds as a double line, and triple bonds as 3 lines. And this is H2. Same thing with F, except in F we have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Boop, boop. They each share 1. We get F bonded to F, so F2. Do these kind of make sense? Last thing about this, I'm hoping the answer was yes, even though no one said anything. The last thing about this is that this direct bond between these 2 atoms is called a sigma bond. Sigma bond, and we use the Greek lowercase letter sigma, which looks kind of like a sideways 6. There's a better example in your book, drawn by a not idiot. But this sigma bond is a direct bond between, like a linear bond between atoms. If there are more bonds, then the second one, the double one, is a pi. And we call it that because it's kind of like above the axis of the bond. So there'd be 1 sigma bond. It doesn't really matter which one. And the other one is a pi bond. And then in a triple, there's 1 sigma in the middle, and then the other 2 are pi's. I'm not sure exactly why they chose these letters to represent. You can look it up. I'll give you bonus points if you write on your test why they chose sigma and pi. But what is true is that the sigma bond is the direct bond between these 2, and the pi bond kind of goes above or below the axis of the rest of the atomic bonding. Your book, for some reason, also chooses to define the vocab words endothermic and exothermic reactions in this chapter. We've talked about those in physical science. We'll talk more about them in the next chapter, but for now, and you know this from your vocab, endothermic is one that absorbs heat energy, and exothermic is one that releases heat energy. The reason they do it in this chapter is because they're talking about bond formation and breaking, and a lot of times the breaking of certain bonds releases energy or absorbs it, and the forming of that same bond will do the opposite one. So, but we'll talk more about that in chapter 9. Do you have questions about this before we move on to polarity, and then we'll do naming? Okay. Hearing none. Let's talk about polarity. I'm going to erase this top line. I'm not going to erase my drawings yet. I'm going to erase my definition of diatomic because we still will need that. But I'm going to head this over here. Polarity. Referring to what? This is a noun, but it refers to the identity of having what? Yeah, poles, like having magnetic poles. This relates to magnetism because a magnet, like a permanent magnet, like an iron magnet, has polarity, and that's the reason it has what we call a magnetic moment. Each little individual atom is lined up, so positive on one side and the negative, and if the whole series of them are lined up like that, that's called a magnetic domain, and if the magnetic domains line up, we call that a magnet. Like we can have a macro scale version of an object that has these properties because of the way its atoms are, which is pretty neat. Anyway, so polarity, if the difference, and there's a chart of electronegativities in your book on page 265, which actually comes in really handy. Let's look at that real quick. Electronegativity. If you're watching this online, Kylo, you can find an electronegativity chart really easily on www.google.com/electronegativity chart. Probably, I assume. I don't know. Just look it up. But what do you notice about the electronegativity chart? These are all arbitrary values. There's not a real unit with these values. They're arbitrary. What atom has the highest electronegativity? First of all, let's define electronegativity. What is it? Well, yeah, there's a little paragraph above it. What is an electronegativity? It says, electron affinity is a measure of the tendency of an atom to accept an electron. And then it says, electronegativity is a value assigned based on electron affinity. So basically it's telling us how badly does this thing, on a scale from 0 to 4, want a new electron. Which one has the highest, do you think? You should know this. Yeah, fluorine. Fluorine's almost 4. It's 3.98. Which one least badly wants an electron? Francium. Yeah, and this relates to the periodic trends that we discussed back in November, maybe? Yeah, I think it might have been chapter 4, maybe chapter 6. I can't remember. It doesn't really matter. But these electronegativities tell us how badly the thing wants another electron. And if the electronegativity values, when we have two things bonded together, that bond's nature is based on the electronegativity values. Turn the page. If it is greater, if the difference between them, I'm going to put that difference. Electronegativity values difference. If it is greater than or equal to 1.7, we call it ionic. It says mostly ionic, but I'm just going to put ionic. 0.4 to 1.7, we call that polar covalent. And then I'm going to skip the next line because I prefer it this way. 0 to 0.4. Well, actually, to be nonpolar it has to be exactly 0. So for it to be 0 would be nonpolar. No difference. How do we ever get no difference here? And then your book uses 0 to 0.4 as mostly covalent, but that's technically polar. Anyway, what does it mean if they have no difference in electronegativity values? It's the same atom. So all these that we just did, all these diatomic ones, non-polar. Non-polar, which means that they don't have magnetic or electromagnetic poles. All of these are non-polar. All the diatomic molecules are non-polar. But it can also be non-polar if, check this out, if I have methane, for instance, which is a C with single bonds to 4 H's. Now each of these bonds is, well, let's just do a little practice one. It would be C, which is 2.55, minus H, which is 2.20, and that's 0.35, so it'd be polar covalent. Each of these bonds is approximately polar covalent, right? You with me so far? But the whole thing, because this one's polar covalent, the electron would rather hang out with the carbon a little tiny bit on each bond. But altogether, where would the electrons rather hang out? The north end or the south end or the east end or the west end of this molecule? It doesn't really matter. Nowhere. So this is also nonpolar because of its physical arrangement. Next thing is we use these little guys, this little lowercase delta, to represent partial positive or partial negative. The classic example of this is oxygen. So if not oxygen, water. So if I have a water molecule, the electrons like to spend their time with oxygen more than with hydrogen, because why? Because there's more what, though? What does oxygen have more of that the electrons like, that they are attracted to? Yeah, the oxygen has more protons. I mean, yeah, you're right, but I'm getting at that the oxygen has more protons, and so the electrons would rather hang out over there. And so there's a partial negative charge. It's not like there's a whole other electron hanging out here. So it's not a whole negative charge, but it's a partial negative charge with, we use this little lowercase delta to represent. And then what makes this interesting is that when we have these polar covalent bonds, then the molecules start to exhibit intermolecular forces. Like this molecule, since just like the nitrogen, it's not probably just all by itself, just one water molecule hanging out. It's got other friends with it. There's probably literally trillions of them, and you need the tiniest little drop of water. So when there's a lot of them together, they exhibit special bonding because the butt end of this, the negative end here, is attracted to the positive end of another one. So they get these bonds that form between them called hydrogen bonds. And that's actually what your book deals with in chapter 14. So we'll leave that at that. But do you see the basis of polar and nonpolar covalent bonds? We already talked about ionic. So these two are different kinds of covalent bonding. The last thing about this is that we say, well, there's this phrase, like dissolves like. Which means that polar substances and nonpolar substances dissolve nonpolar substances. Water and vinegar are both polar, and they're what we call infinitely miscible. We can mix however much vinegar and water together, and we will get a mixture of vinegar and water. But oil is nonpolar, and water is polar, and so we mix them, they separate, and you know that. That's a thing that you have experienced in your life. Gasoline and water don't mix, but oil and gasoline do. So and that's one of the reasons, like if you've been greasing it up at the ranch all day, I assume, if you got grease all over your hands and you want to get them clean, you can use WD-40 or gasoline or something to get it off, or you can use some other organic solvent, but you can't use water. Water won't wash the grease, the tar, the oil off your hands, because it's polar, what's on your hands, and you're trying to use it's non-polar, what's on your hands. You're trying to use a polar solvent, water, to get it off. Questions? You'll have to review this in your book. This was kind of fast, but do you get the basics of electronegativity and polarity? Do you think could you find whether the bond character is ionic, polar, or nonpolar using this math and this chart? Okay, that's what I expect from you. Okay, I'm going to erase all this and we're going to move on to naming. And you already have a naming worksheet, and luckily for you, covalent naming at a basic level is quite a bit simpler than ionic naming, but we're also going to tack on acid naming, which is going to be a little bit more complicated, but that's okay, you'll live. So label this next segment covalent naming, and then start a list. And the list is going to begin with, it's going to be a list of prefixes. And this is going to begin with what, Mitch? Mono. Mono meaning, and your next column is going to say, what does mono mean? 1. Next one is going to be di. Di meaning 2. Where are you getting this information? Just from your brain? Could you get it from the book too? Yeah. Here are the covalent naming prefixes. Go ahead and write them all out. I'm going to write them out up here. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5. Oh yeah, this does to be those really quick. Hexa is 6, hepta is 7, octa is 8, nona is 9, deca is 10, and they do go higher than that, but those are the ones that we're worried about. And really, penta will probably, hexa comes up a little bit, but penta will be the one that's the highest that you usually deal with. But do have them all memorized. And this makes it really, really simple. The only confusing part about this is when to use mono. But let's start with one that doesn't have that. So let's do P2O5. Okay, well, phosphorus, but there's 2 of them, so we say diphosphorus. Oxygen, but there's 5 of them, so we call it pentoxide. They end in vowels, and so if the next thing begins with a vowel, like oxygen or iodine, you just eliminate the vowel altogether. So instead of saying pentaoxide, you say pentoxide. Instead of saying pentaiodide, you'd say pentaiodide. And there are some different conventions for that, but diphosphorus pentoxide. We just put the number of it as a prefix before it. Okay? When to use mono? Well, we usually use mono only if that substance is more commonly something else. So for instance, if we have CO2, we call that carbon dioxide. If we have CO, we could just call it carbon oxide, but there's a more common thing called carbon dioxide, and so we use mono to specifically say that this one only has one oxygen. So we call this one carbon monoxide. Note that we don't put mono on the carbon, because we just already know there's just one carbon. Could you go the other direction? With the ionic ones, we did practice for names going to formulas, and then we did ones for formulas going to names. But doesn't this make enough sense that you could just see this name and then write it out? In fact, that's probably a lot easier, right? So if I put diboron silicide, you'd put B2Si, because it's diboron, 2 borons, silicide, just silicon. The only thing you have to kind of watch out for is when you put mono, and I'm usually pretty lenient on that because it's something you just kind of have to have a feel for. You know, like you have to know whether other elements exist or other compounds exist besides the one you're specifically talking about. I'm going to leave that at that. You will do some more practice on your worksheet. But now let's go on to acid naming. Make sure I'm doing it in the right area. Acid naming. Rule 1, all acids have to have all acids. There are 3 different definitions of acids, but what we call Bronsted-Lowry acids, the simplest definition of acids. All acids have a hydrogen cation. So all of them, every single formula that is an acid, at least the ones we do, is going to begin with H. It might be H2, it might be H3, but it's going to have H at the beginning always, okay? So you have to know that. And that goes the other direction too. If you see something that starts with an H, if you see a formula that starts with H, you know you're going to name it as an acid instead of just as a regular ionic compound. Let's do an easy one. HCl. You see there's an H there. This is called hydrochloric acid. If it's a binary acid, which just means hydrogen and one other element, binary acid. Remember, binary means 2. If it's a binary acid, just hydrogen and another element, we use this prefix hydro, then the name of the other thing, the anion, ic acid. And if that were the only rule, this whole thing would be really easy. What would this be? Hydrobromic acid. What would this be? Hydrosulfuric acid. Hydrosulfuric acid. You're tempted to say sulfic, but it's actually sulfuric. I don't know why it's that way, but hydrosulfuric. But you see what I did here? When I put this formula, I had to match the number of hydrogens to the charge. However, that's really easy because hydrogen's always +1. So if it's with a 2- thing, there's 2 of them. If it's with a 3- thing, there's 3 of them. Where it becomes a tiny bit more complicated, this will be the last thing we do for the whole day, where it becomes a tiny bit more complicated is if we have a polyatomic ion. And not usually for the reasons you think. This is not what throws people off usually. But if we have a polyatomic ion, so these were all binary acids. This is still acid naming, so there, the heading goes for all of it. Now we have polyatomic, I'm sorry, I should be more specific, oxyacid naming. We actually still use the binary rules for cyanide, which is a polyatomic ion. We'd call it hydrocyanic acid. But if it's an oxyacid, this means that it contains a polyatomic ion with an oxygen. So what are some polyatomic ions that have an oxygen in them? You should know these all, so give me 3 examples. So, chlorate. What is another one? bromate. That's another one. Chlorite. Good. I'm glad you chose that one. What we do when it's an oxy acid is, for instance, if instead of these things we had HClO3 and HBrO3 and HClO2, we would change the ic to 8. I'm sorry, it's the other way around, forgive me. 8 to ic and add acid. And if it's us, we change that to, gosh dang it, I did it again. Ite changes to us, and we add acid. So instead of being chlorate, this is now chloric acid. Instead of being bromate, it's now bromic acid. And spell it right, though. So what's the difference between him and him? And how do I know? Well, if all I could see is the name, what's the difference? Yeah, there's no hydro. What's the hydro mean it has to be? Binary acid. The way I think about this is, you ever been to McDonald's? They have a quarter pounder with cheese, and they have a bacon quarter pounder. And the bacon quarter pounder also has cheese, too. They don't say bacon quarter pounder with cheese. The cheese is only important enough to be named if there's not also bacon along, right? The hydrogen's only important enough to be named if there's not also an oxygen hanging out with it. Hydro only gets to be in the name if there's no oxygens around. So any 8 polyatomic ion turns to ic acid, and any ite polyatomic ion changes to us acid. Okay? And you have to be able to go both ways. Name to formula, formula to name, name to formula, formula to name. If I keep doing that, Camden will fall fully asleep and then she'll fall out of her chair. Do you have questions about any of this? You need more practice. We haven't done nearly enough of these for you to be good at it, but where will you get your practice? And? The chapter review. Yeah, you come in too, but that's not going to give you practice. You have a worksheet to do, you have a chapter review to do,